Welcome! In this session, we'll explore a fascinating string manipulation challenge from LeetCode, problem number 1312, minimum insertion steps to make a string palindrome. Together, we'll break down the problem, analyze different approaches, and understand the optimal solution. Let's dive in. The problem asks us to determine the minimum number of insertions required to make a given string a palindrome. A palindrome is any string that reads the same forward and backward, such as Recursion or Madam. To achieve this, we are allowed to insert any character at any position in the string. For example, if the input string is ABC, we could insert characters to make it APBA, which is a palindrome. The input to our problem is a single string S, where its length ranges from 1 to 500 and consists only of lowercase English letters. Our goal is to return an integer that represents the minimum number of character insertions needed to transform the string into a palindrome. Let's look at the first example. If the input string is Zaz, the output is 0. Why? Because Zaz is already a palindrome. It reads the same forward and backward, so no insertions are necessary. Now, consider the second example where the input is Madam. The output here is 2. This is because we can make the string a palindrome by inserting 2 characters. For example, we could add D at the beginning and M at the end, resulting in Dmamadam, which is a palindrome. Alternatively, for the input Madam, we could also insert M after the first M and B after the D, producing the palindrome Badm. Both approaches require exactly 2 insertions. Now, let's examine another example. For the input string LeetCode, the output is 5. This means we need at least 5 insertions to make it a palindrome. For instance, we could add characters to transform LeetCode into LeetCodeoctile or Elatile, both of which are palindromes. In the case of LeetCode, regardless of how the insertions are made, the minimum number required is always 5. This brings us to the constraints of the problem. The string length is between 1 and 500, so our solution must be efficient even for large inputs. Edge cases include single character strings, which are already palindromes and require 0 insertions, or strings that are already palindromes like Recursion, which also need no changes. On the other hand, strings with no repeated characters, such as ABCDEF, may require the most insertions. Testing these edge cases will ensure the robustness of our approach. To solve the problem of finding the minimum number of insertions required to make a string a palindrome, there are several approaches we can consider. One straightforward method is the brute force approach. The intuition here is to try inserting characters at all possible positions in the string and check if the resulting string forms a palindrome. This can be implemented using recursion or backtracking, as we systematically explore all possible combinations of insertions. However, this approach is highly inefficient because the number of combinations grows exponentially with the length of the string. Specifically, the time complexity is approximately 2 to the power of n, which makes this approach impractical for larger strings. While it's conceptually simple, its inefficiency is a major drawback, especially as input sizes increase, rendering it unsuitable for real-world applications or competitive programming settings. A more efficient approach is using dynamic programming, or DP. The key insight here is that instead of trying all possible insertions, we can focus on the relationship between the original string and its longest palindromic subsequence, or LPS. The LPS allows us to determine how many characters in the string already form a palindrome. The minimum number of insertions needed will then be the difference between the total length of the string and the length of its LPS. To calculate the LPS, we use the concept of the longest common subsequence, or LCS, between the string and its reverse. For implementation, we define a DP table where DP, I, J, represents the length of the LPS in the substring from index I to J. The transition relation depends on whether the characters at the boundaries match. If they do, we extend the LPS by considering the inner substring and adding 2. If they don't match, we take the maximum LPS length possible by either excluding the first or the last character. Base cases handle substrings of length 1, where the LPS is simply 1. This approach is significantly more efficient, with a time complexity of n squared and a space complexity of n squared, making it well suited for larger input sizes. To further optimize the DP approach, we can reduce its space complexity. The 2D DP table used in the previous solution requires n squared memory, but we observe that at any given step, we only need information from the current row and the previous row. This allows us to replace the 2D table with two 1D arrays, one storing the current values and the other storing the previous values. This space optimization reduces the memory requirement from O(n) squared to O(n), while the time complexity remains O(n) squared. The dynamic programming approach was chosen as the preferred strategy for this problem because it strikes a balance between efficiency and clarity. While brute force is infeasible due to its exponential complexity, and the space-optimized DP variant is more memory efficient, it can be slightly less intuitive for beginners. For teaching purposes, the full 2D DP implementation is often favored, as it provides a clearer visualization of the problem-solving process and the relationships between subproblems. The dynamic programming solution is the most practical and efficient way to solve this problem, as it balances time and space complexity while being relatively straightforward to implement. By leveraging the relationship between the original string and its longest palindromic subsequence, we avoid redundant computations and transform the problem into a well-understood one. This approach ensures that we operate efficiently within the given constraints and is robust enough for large input sizes. Ultimately, it provides a structured and elegant methodology for tackling the challenge of making a string a palindrome with the minimum number of insertions. In this problem, we are tasked with finding the minimum number of insertions needed to transform a given string into a palindrome. A palindrome, as you know, reads the same forward and backward. Our goal is to achieve this transformation by adding as few characters as possible. To solve this efficiently, we use a dynamic programming approach. The key insight here is that the problem can be reduced to finding the longest palindromic subsequence, or LPS, within the string. Once we determine the LPS, the difference between the length of the string and the LPS will directly give us the minimum number of insertions required. Let's break this down step by step. First, we define a DP table where DP, I, J, represents the minimum insertions required to make the substring from index I to J a palindrome. For our base cases, if I equals J, we know that a single character is inherently a palindrome, so no insertions are needed, and DP, I, J, is 0 in this case. If I is greater than J, the substring is invalid, so we don't compute any value for it. Now, for our recursive relationship, consider the characters at indices I and J. If these characters are the same, no new insertion is required at this step, and the value of DP, I, J, simply equals the value of DP, I plus 1, J 1. However, if the characters are different, we need to insert one of them to make the ends match. This gives us two options: either insert a character at the JTH position to match S, I, or insert at the ITH position to match S, J. In either case, we add 1 to the result of the smaller subproblem. Mathematically, this is expressed as dp, I, J, equals 1 plus min, dp, I plus 1, J, dp, I, J 1. Finally, we compute the values iteratively. Starting with substrings of length 2, we progress to longer substrings, incrementally solving for each possible range using nested loops. The outer loop iterates through the lengths of substrings, and the inner loop iterates through their starting indices. At the end of the computation, the value stored in dp, 0, and 1, which corresponds to the entire string, represents the minimum number of insertions needed to make the string a palindrome. This approach is rooted in the idea of transforming the problem into finding the longest palindromic subsequence, or LPS. The difference between the total length of the string and the LPS gives us the exact number of insertions required to fill the gaps between non-palindromic characters. Additionally, the symmetry of the DP table allows us to optimize the computation. Since each value in the table depends only on smaller substrings, we can iteratively fill the table without recursion. The time complexity of this approach is O(n) squared, due to the nested loops used to fill the DP table, and the space complexity is also O(n) squared, for storing the table. However, space can be reduced to O(n) using a rolling array technique, as only the previous row is needed at any given point. To implement this solution, we use a 2D DP table where each cell dp, I, J, holds the minimum number of insertions required for the substring S, I, J. The input string itself is used for comparisons, such as checking whether S, I, equals S, J. Let's walk through an example to see this approach in action. Suppose the input string is S equals APCA with a length of 4. We begin by initializing the DP table. All diagonal entries, which represent substrings of length 1, are set to 0 because a single character is already a palindrome. Next, we compute values for substrings of increasing lengths. For substrings of length 2, we compare adjacent characters and update the table based on whether they are equal or not. This forms the basis for solving longer substrings. For instance, consider the substring S0, 1, which is a b. Since a and b are not equal, we compute dp0, 1 as 1 plus min dp1, 1 dp0, 0, which equals 1. Next, for substrings of length 3, we compare characters at the ends and use the recursive relationship to fill the table. For example, for the substring S0, 2, or ABC, we compare S0 and S2. Finally, for the full string S0, 3, or APCA, we compare S0 and S3. Since these are equal, no insertion is needed at this step, and the value of dp0, 3 equals dp1, 2, which is 1. Thus, the minimum number of insertions needed to make APCA a palindrome is 1. For example, inserting a b at the end transforms the string into APCA, which is a palindrome. This implementation solves the problem of finding the minimum number of insertions required to make a string a palindrome using dynamic programming. We start by initializing a 2D DP table where dp, I, j, represents the minimum number of insertions needed to make the substring s, I, j plus 1, a palindrome. The table is initialized with zeros since no insertions are required for single-character substrings, base case. The outer loop iterates over possible substring lengths, starting from 2 up to the length of the string. For each substring length, we calculate values for all possible substrings of that length by iterating over their starting index I. The ending index j is determined as I plus length 1. For each substring s, I, j plus 1, if the characters at both ends, s, I, and s, j, are equal, no new insertions are required. We simply inherit the value from the inner substring s, I plus 1 and j, i.e., dp, I plus 1, j1. If the characters at the ends do not match, we consider two options, adding a character to match s, I, at the end or adding a character to match s, j, at the beginning. The minimum of these two options is taken, and 1 is added to account for the new character insertion. Finally, the value dp, 0, and 1, top right corner of the dp table, contains the result for the entire string, as it represents the minimum insertions needed for the substring s, 0, n. The algorithm has a time complexity of O, n squared, due to the nested loops filling the dp table and a space complexity of O, n squared, for the table itself. This efficient solution ensures that we can handle strings of reasonable length within competitive programming constraints. This is the Java implementation of LeetCode problem number 1312, minimum insertion steps to make a string palindrome. The logic mirrors the Python solution, using dynamic programming to calculate the minimum insertions required to transform a string into a palindrome. Key differences include the use of Java's type system and arrays instead of Python lists. The dp table is represented by a 2D integer array, and the solution iterates through substrings of increasing length to fill the table. The result is obtained from dp, 0, and 1, representing the entire string. In this problem, the objective is to find the minimum number of insertions required to convert a given string into a palindrome. A palindrome is a sequence that reads the same forward and backward. To solve this, we use a dynamic programming approach. First, we initialize a 2D dp table dp of size nxn, where n is the length of the string. Each entry dp, I, j, will represent the minimum number of insertions needed to make the substring s, I, j plus 1, a palindrome. For the given example, s equals APCA, the length of the string is 4. We start filling the table by processing substrings of length 2. For instance, for the substring from index 0 to 1 is 0 equals at and s, 1 equals b. Since the characters are not equal, we calculate dp, 0, 1 equals 1 plus min, dp, 1, 1, dp, 0, 0 equals 1. Similarly, for substrings from index 1 to 2 and 2 to 3, we find that the characters do not match, so the respective values of dp are also calculated as 1. Now, we move on to substrings of length 3. For example, for the substring from index 0 to 2, s, 0 equals at and s, 2 equals c, the characters are not equal, so dp, 0, 2 equals 1 plus min, dp, 1, 2, dp, 0, 1 equals 2. Similarly, for the substring from index 1 to 3, since s1 equals b and s3 equals or are not equal, we calculate dp1, 3 equals 1 plus min, dp2, 3, dp1, 2 equals 2. Finally, for substrings of length 4, we check the entire string s from index 0 to 3. In this case, s0 equals and s3 equals or are equal, so no additional insertion is needed at the boundaries. We set dp0, 3 equals dp1, 2 equals 1. This final value represents the minimum number of insertions required to make the string a palindrome. Let's consider another example where s equals race. The length of the string is 4, so we initialize a dp table of size 4x4. Starting with substrings of length 2, we compare adjacent characters. For instance, for s0 equals and s1 equals since they are not equal, dp0, 1 equals 1. Similarly, for s1 and s2 and s2 and s3, the characters differ, so dp1, 2 and dp2, 3 are both set to 1. For substrings of length 3, we calculate values like dp0, 2 by considering s0 equals and s2 equals c, which are not equal. Here, dp0, 2 equals 1 plus min, dp1, 2, dp0, 1 equals 2. Similarly, for dp1, 3, the characters s1 equals and s3 equals e are also unequal, so dp1, 3 equals 2. Lastly, for the full string of length 4, since s0 equals and s3 equals e do not match, we calculate dp0, 3 equals 1 plus min, dp1, 3, dp0, 2 equals 3. This tells us that 3 insertions are needed to make s equals race a palindrome. Finally, let's look at a simpler example where s equals aa. Here, the length of the string is 2, and we initialize a dp table of size 2x2. For the single substring s0:2, we compare s0 and s1, which are both equal to a. Since the characters already match, no insertions are needed, and we set dp0, 1 equals 0. This means that the string is already a palindrome, and the minimum number of insertions required is 0. By using this dynamic programming approach, we can systematically solve for the minimum insertions in strings of varying lengths and complexities. In this solution, we use dynamic programming to determine the minimum number of insertions needed to make a string a palindrome. First, we initialize a dp table with dimensions nxn, where n is the length of the input string. This initialization step involves filling all n-2 entries with an initial value, which requires n² time. Next, we populate the dp table using a nested loop structure. The outer loop iterates over the possible lengths of substrings, starting from 2 up to n. For each substring length, the inner loop processes all valid starting indices I, with the ending index j computed as I plus length 1. For every I-j pair, we perform a comparison and update the dp table with the minimum number of insertions required. While the number of iterations for the inner loop decreases as the substring length increases, the algorithm ensures that all necessary substrings are evaluated efficiently. Now, let's quantify the total number of iterations involved in filling the dp table. For substrings of length 2, there are n1 possible starting points. For length 3, there are n2 starting points, and so on, until for length n, there is just one substring. Summing these values forms an arithmetic series, n1 plus n2 plus 1, which simplifies to n*n1/2. This sum evaluates to n² in terms of time complexity. Therefore, combining the initialization of the dp table and the process of filling it, the overall time complexity of the algorithm is n². This quadratic complexity is a significant improvement compared to a brute force approach, as we will discuss shortly. The space complexity of this solution is also determined by the use of the dp table. Since the table has dimensions nxn, it requires n² space. Aside from the dp table, the algorithm uses a few auxiliary variables, such as those for loop indices and intermediate computations, which together consume O1 space. No additional data structures are introduced, so the overall space complexity is n². When comparing this dynamic programming solution to a brute force approach, the difference is striking.
A naive method would involve exploring all ways to insert characters and checking if the resulting string is a palindrome.
This approach has exponential time complexity, 2 to the power of n, as each character introduces two choices. Dynamic programming, on the other hand, avoids redundant computations by storing intermediate results, reducing the time complexity to n squared, while maintaining the same space complexity.
Finally, let's analyze the algorithm's performance across best, worst, and average cases.
In the best case, where the input string is already a palindrome, the algorithm still computes all entries in the DP table, resulting in n squared time complexity. Similarly, in the worst case, such as a string with no matching characters like ABCD, the algorithm must evaluate all substrings, leading again to n squared complexity. For average cases, regardless of the input structure, the algorithm processes all substrings similarly, maintaining a consistent n squared time complexity. Mathematically, the DP table contains n squared entries, and each entry is computed in 1 time by performing a comparison and a minimum operation. This confirms the overall time complexity is n squared. Additionally, since the DP table is the only major data structure used, the space complexity is also n squared.
When tackling this problem, there are several common mistakes to watch out for. First, confusing minimum insertions with minimum deletions is a frequent error. Although the two might seem similar, they are fundamentally distinct. Insertions involve adding characters to the string, while deletions require removing them. Solving for one does not directly translate to solving the other.
Another common issue is misunderstanding the relationship between the longest common subsequence, or LCS, and palindromes. This problem can be reduced to finding the longest palindromic subsequence, or LPS, which can be solved efficiently using an LCS-based approach. Without recognizing this connection, you might resort to less efficient techniques, such as recursive backtracking, which can lead to exponential time complexity. Finally, be mindful of edge cases. For example, strings that are already palindromes, like ABBA, or strings with only one character, require minimal work. Failing to handle these cases can result in unnecessary computations or incorrect results for simpler inputs. Another pitfall to avoid is relying on inefficient recursive solutions without memoization. Plain recursion often leads to redundant calculations, especially for overlapping subproblems, resulting in exponential time complexity. This approach will fail for larger inputs due to time limits or stack overflow errors. Additionally, it's important to set up the base cases for your dynamic programming table correctly. Errors here, such as initializing invalid values for substrings of length 1, can propagate through the DP table, leading to inaccurate results. Both of these mistakes highlight the importance of careful implementation and understanding of the underlying algorithm to ensure correctness and efficiency. Now, let's focus on some key insights and strategies for solving this problem effectively, especially in an interview setting. At its core, the task is to determine the minimum number of insertions required to make the string a palindrome. This can be simplified to an LPS, where LPS is the longest palindromic subsequence. Recognizing patterns is crucial here, as many palindrome-related problems can be approached using dynamic programming based on substring properties. The optimal method involves constructing a DP table to compute the LPS in n squared time. From there, the difference between the string length and the LPS gives the answer. While some candidates might attempt a two-pointer approach, it's important to note that this is only effective for specific cases and is generally suboptimal. When discussing brute force or recursive approaches, be sure to communicate the trade-offs. These methods are often easier to grasp but lack the efficiency needed for larger inputs, making dynamic programming the preferred solution. Finally, it's helpful to understand how this problem connects to related challenges. For example, the longest palindromic subsequence problem, LeetCode number 516, is directly tied to this solution, as is the longest common subsequence problem, LeetCode number 1143. Other related problems include palindrome partitioning 2, LeetCode number 132, and edit distance, LeetCode number 72, which also involve dynamic programming techniques. Now, let's briefly compare alternative approaches. A purely recursive solution involves trying all possible insertions, but this results in exponential time complexity, making it impractical for larger strings.
A dynamic programming approach, on the other hand, uses a DP table to calculate the LPS and derives the minimum insertions as n LPS. This method achieves O(n squared) time complexity, though it requires O(n squared) space. For those seeking further optimization, a space-optimized DP approach reduces the memory usage to O(n) by storing only the current and previous rows of the table. While this is slightly more complex to implement, it offers significant benefits in terms of space efficiency, making it an excellent choice for larger inputs. Great job! We've successfully tackled the minimum insertion steps to make a string palindrome problem. Remember, dynamic programming is a versatile approach for solving string-related challenges. Keep practicing and exploring. Thank you for watching. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!